In example 4, we're going to be solving an application involving uniform motion. In these types of problems, with the uniform motion problem, we use the formula from physics, distance is equal to rate times time, or some kind of algebraic equivalent to that. Say we wanted to solve this for t, time is equal to distance divided by rate. And I got that by dividing both sides of this equation by r. Okay? If you need to solve for r, you divide both sides by t. But that's the formula you need to know. Keep that in mind. Let's read our example. Barbara drives between Miami, Florida and West Palm Beach, Florida. She drives 50 miles in clear weather and then encounters a thunderstorm for the last 15 miles. She drives 20 miles per hour slower through the thunderstorm than she does in clear weather. Probably a good idea to slow down. If the total time for the trip is 1.5 hours, determine her average speed. We're looking for a rate here. What's her average speed in nice weather and what's her average speed driving in the thunderstorm? Remember, on these types of problems, it's helpful to set these up in a table. I'm going to compare her nice weather trip versus her during the thunderstorm trip. So in the second row here, I'm going to talk about her nice weather. And then we're going to discuss what happens with her driving in the thunderstorm. And we want to discuss quantities about the distance, the rates, and the times. So let's make columns for those. Distance, rate, times. All right, that looks pretty good. Now, let's pick out the information and fill in the cells within our table as much as we can. As far as the distances go, we know that she drives 50 miles. There's a label for a distance in the clear weather. So her distance in the nice or the clear weather is 50 miles. And if you want to put the label miles there, you sure can. And then during the thunderstorm, she drove for 15 miles. That's her distance in the thunderstorm. Okay? Now, we do have a comparison between her rates. We also know the total time is an hour and a half. What we are looking for is what is her average speed in nice weather and her average speed driving in the thunderstorm. Well, if we let x, that's what we're looking for, is the rate or the speed. That's going to be equal to our average speed in the nice weather. Because she slowed down 20 miles per hour in the thunderstorm, her speed in the thunderstorm is x minus 20. Right? She slowed down 20 miles per hour there. Now, once you get 2 of the 3 columns filled out, we're going to fill that third column out using the other 2. Now remember above we said that time is equal to the distance divided by the rate. So we're going to be able to fill out this time column by taking the distance divided by the rate. So the time that she spent in nice weather can be expressed as 50 over x. And the time that she spent during the thunderstorm is her distance divided by her rate. That is 15 over x minus 20. Now we're going to use this information in the time column to set up our model. We do know, recall, that the total time for the trip is 1.5 hours. Okay? And so we know that her time in the nice weather, I'll call that T sub n, added to the time in the thunderstorm, that adds up to 1.5 hours. So her time in the nice weather is 50 over x. The time in the thunderstorm is the 15 over x minus 20. That's equal to 1.5. Now, we have our model set up, and it has one equation with one unknown. Now it's just a matter of solving this equation. Okay? First of all, let me go ahead and say x better not be equal to 0 or 20. Because those quantities won't check. It'll give us 0 in the denominator of our fraction. The next thing we're going to do is clear out fractions by multiplying through by the least common denominator. In this case, the least common denominator is a factor of x times a factor of x minus 20. So I'm going to multiply all three of my terms, even the right-hand side, by x times x minus 20. There, here, and also on the right-hand side. All right, let me scroll a little bit here, and we will cancel common factors. First of all, our x's will reduce, leaving us with 50 times the quantity x minus 20. Bring down the plus sign. Reduce the whole factor of x minus 20 with this whole factor of x minus 20, and we're just left with 15 times x. Now, on the right-hand side, let me go ahead and run 1.5x through to both of these terms. 1.5x times x is 1.5x squared. Quadratic. And then minus 1.5x times 20 is minus 30x. Okay? Now it's a matter of cleaning this up and getting everything on one side equals 0. And I think I'm going to move everything to the right-hand side. So first of all, run the 50 through on the left-hand side. We'll have 50x minus 1,000 is 50 times 20 plus 15x equals 1.5x squared minus 30x. All right, let's see. 50x and 15x is 65x. So let me go ahead and subtract 65x from both sides. And let me add 1,000 to both sides. So I have everything on one side over here equals 0. Okay? Now, like I said, the 50 plus 15 is 65 minus 65x. That leaves us with 0 on that left-hand side. On the right-hand side, we have 1.5x squared minus 95x plus 1,000. Now, with that weird lead coefficient of 1.5, I'm not seeing how this might factor. It could, okay? But instead of spending my time figuring out how that would factor or unfoil, I think I'm just going to plug it into my quadratic formula. There's my A value, there's my B value, there's my C value. So, we have x is equal to negative 95, negative B, and y'all can go ahead and just write plus 95 right there, just 95, okay? Plus or minus the square root of negative 95 squared. Punch that into your calculator. Negative 95 squared is 9,025. minus 4 times the A value of 1.5 times the C value of 1,000. All over 2 times the A value. 2 times 1.5 is actually 3. And you can write 2 times 1.5, and then the next step you can get 3, whatever. All right, so let's actually get this simplified a little bit. Okay, so X, which remember that means her speed. X is her speed in the nice weather. That's what we're solving for. We have 95 plus and minus the square root of something, all divided by 3. So now on our calculator, we're going to have 9,025. Let me work underneath here. I've got 9,025 minus 4 times 1.5 is 6 times 1,000 is going to be 6,000. So 9,025 minus 6,000 is 3,025. Okay, now if you want to go ahead and take the square root of 3,025, see if that's something nice, that would be helpful. Either way, we're going to go ahead and split this up, one with the plus and one with the minus. So we have a potential usual speed of 95 plus, actually the square root of 3,025 comes out to be 55. Did y'all get that in your calculator? Well, you would, okay. So we've got 95 plus 55 divided by 3. And we will also have with the minus 95 minus 55 divided by 3. Okay? So 95 plus 55 is 150. When we divide that by 3, we get 50. And that is actually miles per hour in the clear weather. Okay? And then on this one, 95 minus 55 is 40. 40 divided by 3 ends up to be 13.3. If that is her speed in the clear weather, when she slowed down 20 miles per hour when the thunderstorm came up, she would be going negative, like 6.7 or whatever that is, miles per hour. So this one won't work. It won't check. We're going to use the 50 miles per hour in clear weather. That means how fast is she going in the thunderstorm? Well, remember, she slowed down 20 miles per hour when the thunderstorm hit, so 30 miles per hour in the thunderstorm. That's her average rates in each of those scenarios.